In some cases, we may need to use multiplication, and it typically comes through with wording of and connecting to events. Or more often than not, it should be translating to the idea of and then. As we talked about in a previous video, you want to be careful of when you use multiplication and not multiplication, because we looked at the case of where you can see the word and when you're talking about a single thing with two characteristics. So, like in the case of the jelly beans, one jelly bean that's both blue and purple, or both green and red. So one thing having two characteristics, and with that you find the probability pretty directly in terms of how many things have both the characteristics out of your total number of outcomes. Or in terms of in a table, it would look like a joint probability, in that you would look for where do they intersect out of your total number of outcomes. So just be careful that when you see the word and, it's not always multiplication. You have these two scenarios. So we've looked at examples with that first scenario there, but now this is a second scenario that can come through. And what's key to recognize is that this is coming from a sequence of events. So typically we'll have kind of a number of trials, and then it's this probability of seeing certain results for certain trials. So let's look at this with jelly beans. So we have our 10 jelly beans that we've been working with, and what we're going to do is draw 2 jelly beans. So that's another sign that you might be using multiplication rule, is that typically you have more than one event occurring. So in this case, we have 2 events. Event 1 is going to be drawing the first jelly bean, and then we're going to draw a second jelly bean. What we also want to recognize is that we're doing this with replacement, which means we're going to have independence. And it's going to be important to recognize whether or not we have independence, because if we're looking across events, if we have independence, then probabilities aren't going to change. We're not going to have to worry about them. But if we don't have independence, that means the probabilities are changing with each event, and we need to adjust for that. So we're going to look at examples of both cases here. So what's the probability of choosing a green jelly bean? And then because this is a sequence of events, this is going to lead to some multiplication, and then a red jelly bean. So in our notation, we write it as probability of green and red, which is confusing because it's not showing this idea of actually it's saying and then. So that is in there, that this is a sequence of events, and we want to look at green and red. And you could also think that this is describing a sequence in terms of this is what'll happen for event 1, and this is what'll happen for event 2. So the notation itself can look kind of confusing, but again, it's a sequence of events. So what we can do here is with multiplication, and because we have independence, we can just take what's the probability of getting a green jelly bean multiplied with what's the probability of getting a red jelly bean. So we'd be taking 3/10 times 4/10, which will give us a 0.12. So there is a 12% chance of drawing a green and then a red jelly bean. With replacement. Because we put that jelly bean back when we went to event 2, because it is a sequence. You could think that this first event, that probability of green occurred. So we're choosing our first jelly bean. What's the probability of it being green? There's 3/10. But then when we go to the next event, this probability of a red jelly bean, we need to think about what's the probability of red with our bag of jelly beans. But since we put that first green one back, it's still 10 jelly beans, same distribution of probabilities, so that stays 4/10 there. Let's look at another example of this. Say we're drawing with replacement, so we have independence. so probabilities aren't going to be changing here. And what's the probability of a red jelly bean and then a purple jelly bean? So we're looking for the probability of red and then purple. And we can just multiply this probability of red times probability of purple, which red is the 4 out of 10 and purple is 2 out of 10. So this is going to be a 0.08. So there's an 8% chance with this. All right, so this is our multiplication rule. What's key is that this multiplication rule is specific to independent events. But if you're looking for the probability of event A and then event B, so just make sure that notation is describing event A and then event B. You can just multiply the two probabilities. So let's talk about what if we had without replacement. If we didn't put the jelly beans back. So this is where we are not independent, meaning the probabilities are changing. In fact, let's draw our bag of jelly beans. Let's see, we have 1 blue, 2 purple, 3 green, 4 red. So we have our jelly beans. So what's the probability of choosing a green and then a red jelly bean? So we're still going to use multiplication here, but what's going to change is how we calculate our second probability. So we are going to look at probability of event 1 times probability of event 2. So event 1 is just choosing our first jelly bean, which means we start with this bag of jelly beans, and what's this probability of choosing a green jelly bean? Well, it would be the 3 out of 10. So that first probability is pretty much just the same as probability of green. What changes is when we get to event number 2, because we've chosen this green jelly bean and now it's not in the bag anymore. So what we have is this new distribution of probabilities because we didn't replace it. So we want to know the probability of red, and we want to think about the probability of red with this new bag, which would mean we have these 4 possibilities out of the 9 jelly beans, which would be 0.1333 when we multiply those together. But it comes out to this multiplication of probability of green times this probability of, and we want to calculate this red given a green was removed. And in the next module, we'll talk much more about this idea of given events. This is coming through as a conditional probability. It's conditional because there's this condition that has already occurred, but we'll talk more about that. In terms of right now, we can think visually in terms of how this distribution changes by removing one thing. So let's try this again. Say we have our bag of jelly beans. We have a blue, 2 purple, 3 green, 4 red. And we want this probability of choosing a purple and then a green. So because we're working without replacement, it's not independent. So with that first probability, taking just the probability of purple times, and then we want to think about this probability of green given a purple was removed. So our first probability, take out one of the purple, which is 2 out of 10 chance of that occurring. And then we'll just remove that one, times green. There's 3 green jelly beans out of the 9 remaining. So if we calculate this, it'll be a 6 out of 90, which will be a 0.0667. So 6.67% chance of occurring. We made our sentence there. So this is the difference between independent and not independent events. When it's independent, straightforward, just multiply the two probabilities. when they're not independent, you have to think about this conditional probability for the second piece. Something you can do to prove independence is you can use this formula here. Meaning, if you have the information for both sides of the equation, if you take this probability of both and it's same as the multiplication, then you have independence. But if you say plugged in everything that you know about your situation and they ended up being not equal, say you had this probability of both and took the probability of the multiplication, if those are equal, it's independent. If they're not equal to each other when you plug in both sides, then you have that it's not independent. So you can use that formula there. Something that can come through to prove independence is this 10% condition, which says when we sample less than 10% of the population, the probabilities can be assumed to be independent. So if we go to a very large scale for this question, just to kind of prove why this works. Say we're looking at Americans and we want to find the probability of selecting 2 Americans with blue eyes, given that 17% of Americans have blue eyes. So we're going to have this probability of blue eyes is a 0.17. So if we're working with people and we're looking at this probability of blue and then a second person having blue eyes, this is working without replacement. We probably won't want to choose the same person twice in this scenario. So what you do is randomly select a person, they have blue eyes, and then put them off somewhere and then choose your second person. So this would be without replacement, which would mean the probabilities would technically change. So let's see, 17% of 327.2 million is going to be a lot of people. I'm not going to calculate the exact values here because what we're going to find is that we actually don't need them. But what we would technically have to do, since we're working without replacement, is get the number of Americans with blue eyes out of 327.2 million. And then multiply that with, and then you'd think about the adjustment, like number of Americans with blue eyes, but then take out one of them over 327.2 million minus 1. Since we're working with such large numbers here, this subtraction of 1 isn't really going to do anything. Where this first probability is going to be 0.17, and then we're multiplying, just by taking 1 away from the numerator and denominator, this is basically still going to be 0.17. And the idea is that we've only done this process 2 times. Basically, our number of trials, if we compare 2 to this 327.2 million, that sampling of 2 is less than 10% of our population. It's less than 10% of that 327.2 million. So it's this concept that we can use of if we're sampling just a small portion of something very large, and we can use this 10% as kind of the cutoff, then really this taking away of 1 from the numerator and denominator isn't going to change things. So what we can use is, instead of, even though it's without replacement, we can assume independence. Instead of thinking of taking 1 away, just multiply the 2 probabilities together. Take probability of blue times probability of blue to get the solution out. So 10% condition, something we can use. It's mostly helpful when we're trying to work with a very large population.